Hey there guys, welcome back. We're going to be looking at our gas law section here, starting with a problem like number 12. These types of problems, you're going to be using your gas law equations, so make sure you're looking back at the handy dandy list of equation sheets here for us. In this problem, you might notice that we've got a rigid container with a volume of 23 liters. And the gas inside has a pressure of 107 kPa at 43 degrees Celsius, and we're going to decrease that pressure to 83 kPa, and we're looking for that new temperature in Celsius. The last part's going to be important. We'll get to it. So we notice here that we've got a changing pressure and a changing temperature, so that tells me we're going to be using Gay-Lussac's law. We have a P1 over T1 equals P2 over T2. Okay, you could go ahead and plug your numbers in here, but I'm going to go ahead and rearrange my equation with some cross multiplying and see that I have P1 times T2 is going to be equal to our T1 times our P2. Alright, so then lastly, if I'm looking for that new temperature, that T2, I'm going to divide over my P1, and I'm going to have my T2 equals the T1 times P2 over P1. Okay, let's plug in our values. And remember, we're not going to just plug in 43 because anytime we do a problem in a gas law, we want to make sure we convert to our friend Kelvin. So the temperature in Kelvin for 43 is going to be 316 degrees Kelvin. And then I'm going to plug in my P2. That was the second pressure after I decreased. So that's going to be the 83 kPa. And then lastly, I'm going to put in my initial pressure, the P1. That's the 107 kPa. So I'm going to plug this into my calculator, and I'm going to get 316 times 83 divided by 107. So you might be tempted to just put that answer down of 245, but you want to remember that this problem asked for this in Celsius. So this number, this 245, this is not in Celsius. This, because kPa's cancel, this is in Kelvin. So in order to get to Celsius to Kelvin, I would add 273. To go from Kelvin back to Celsius, I'm going to subtract 273, and we're going to end up with a temperature of negative 27 degrees Celsius. If you want to round, you could do 27.9 degrees Celsius as our final answer here. And excuse me, right there. So it's negative 27.9. Okay. I also want to talk about another calculation problem down here with number 14. Here we're calculating our number of moles of gas. Right away, that should ding off some bells in your head and tell you that we are not going to be using things like our Gay-Lussac's. We're going to be using our ideal gas law, right? Because the N here stands for moles. So you're looking for your moles. Okay? You're given a pressure. We're given a volume. We're going to make sure to convert that to liters. And we're given a temperature that we're going to convert to Kelvin. Okay, so knocking off our stuff there, we've got PV equals nRT. And we can rearrange this guy so that we have our N equals, divide over the RT, equals PV over RT. We know our pressure. We know we can find our volume in liters. We know our temperature. Last thing to think about there is what is that R value? Now you're going to want to make sure that your R value in this problem is going to match your units. We have three possibilities. Which one is it going to be? We're going to use the one with kPa because that matches the units of our pressure. So our R value in this problem is going to be 8.31. And these guys have these big fancy units of kPa times liters over moles degrees Kelvin. So this gets plugged in and you can solve for your N value. You should end up with a correct answer of right around 0.002 moles. Okay, so you can set all these up and give them a try and finish up your gas law section on your own. All the other answers are up on Haiku. Good luck the rest of your day, guys. Have a good one.